Okay, so today we will begin uh, chapter 4, which is transient analysis. Right. So in chapter 3, we looked at capacitors and inductors. We looked at steady state conditions. We studied the equations that relate uh, voltage and currents for both capacitors and inductors. Now let's look at. oh, Let's bring up new share right there. Okay, is it visible to all online? All right, thank you. Okay, so transient analysis, right? Chapter 4. In chapters 3 and 4, in chapter 3, we learn how capacitors and inductors are energy storage elements because they receive energy and they can release it back into the circuit at a later period in time, right? This energy transfer back and forth requires a finite amount of time. It cannot take place instantaneously. And so during that portion where the energy is either being received or being transferred back out, the voltage and current for a capacitor and inductor always changes with respect to time. So it has a different value with respect to time. So before it begins receiving the energy, whether the stored energy in the capacitor or the inductor was zero, or whether it was at a certain level, we say that it was at a steady state, right? Because the voltage and current was steady with respect to time. It did not change. Now, once it begins receiving the energy, that voltage or that current has a different value at any given point in time. And that response is known as the transient response because it is fleeting, it is momentary. It could take microseconds, it could take milliseconds, it could take a few seconds. But eventually, that response will vanish. And once all of the energy is received, and we say that the capacitor or inductor has reached maximum charge or full charge, the voltage and current again has a value that is steady with respect to time. And so that again is known as steady state. So before it begins charging or after it's completely discharged, it is known as steady state. But between those two time periods, we have what is known as transient portion or transient analysis. And that is what we're going to study. So inductors and capacitors are energy storage elements. If you have one energy storage element in a circuit, we say, or not we say, it requires the solution of a first order differential equation. And we say that the circuit is a first order circuit. A first order circuit. Now, when I say one energy storage element, it does not mean physically one. It just means schematically it could be one. And the difference is physically it could be more than one component. It could be hundreds of components, could easily be thousands or millions of components. The crucial point is that it should be reducible to one single component. Meaning if you have a bunch of capacitors in series or inductors in parallel, and if it is possible to reduce it down to one single equivalent capacitance or inductance, then schematically we can still refer to that circuit as having one energy storage element. Does that make sense to all of you, right? So it's basically CEQ or LEQ, as you will soon see in the next few slides. Okay, so if it is reducible down to one single element, it is still referred to as one energy storage element, which provides solution of a first order differential equation, and hence it is known as a first order circuit. Now, typically, these circuits will involve inductors and resistors, or capacitors and resistors, and hence we call them as RL or RC circuits. And these are first order circuits. First order circuits. If it is not possible to reduce, if you have more than one inductor or one capacitor, you have now two energy storage elements, and two energy storage elements requires a second order differential equation, and so it is known as a second order circuit. Now, typically when we study these circuits, we take the typical examples like RL, RC, and we take a third example known as RLC, which would be a second order circuit. Now, I don't know about you, but solving differential equations is not on my list of fun things to do, right? I'm sure pretty much every one of you is much better than me at math. It's not one of my favorite topics, especially engineering math. Anyway, so we will talk about and look at equations for RL and RC. I will introduce the topic of RLC circuits, because RLC circuits, I think it's well, we'll introduce the topic, but I think it's a little bit much for a non-E major class. But again, I will talk about that, what it involves. Now let's see. Okay, so transient phase, right? Transient phase is when energy is being transferred back and forth from the inductor or capacitor with respect to the source or the circuit, right? When the energy is being received by the components, we say that the components are being charged. And when the components send the energy back into the circuit, we say they are being discharged. Okay, and there's a specific technical name for each one of those processes. And the analysis of the circuits during those phases is, of course, transient analysis. So based on whether we are charging or discharging, there are two kinds of responses. One is known as the natural response. The other one is known as the forced response. Now, it is not as sinister as the word sounds. Okay. Everything that we have studied so far is basically forced response. And it's so called because you have an external source connected to these components. Basically, every resistive circuit that we have seen, we have a source connected to those resistors. So the voltage or current that is generated in those resistors or in those capacitors or in those inductors is forced due to the application of an external source, right? If we don't have a source, we don't have a voltage or current. So everything that we have studied so far is forced response. The new thing that you're going to study is basically natural response, right? So forced response is basically when you connect a source to a circuit and it's receiving the energy, charging phase. When the source is removed and the only thing that left in the circuit are resistors, all of the energy is now transferred to the resistors. The resistors dissipate the energy in the form of heat, and that is known as the natural response. It is so called because the voltage and current for that capacitor or inductor does not depend on any external source. It is naturally occur. Well, even though that energy comes from outside, at that point of analysis, that voltage or current is naturally present inside the capacitor or inductor. Does that make sense to everyone? The difference between a natural and a forced response, right? So natural is basically discharging, and forced is basically charging, right? Now, when we plot the voltage or current for both charging and discharging, it turns out that they have the exact same form. It is exponential in nature. That makes things simpler. So, two common graphs about charging. This one is for voltage, and this one is for current. Now we can solve and analyze for voltage and current for both inductor as well as capacitor. But for convenience purposes, we will write voltage equations for capacitor and current equations for the inductor. Okay, current equations for the inductor. And we will see that the equations have a very similar form. Here, x-axis, which is always time, could be milliseconds, microseconds, could be seconds. It'll be given in the problem itself. And this is 0, meaning the point at which you begin your analysis. Okay, so time t equal to 0 is simply the point at which we begin our analysis. That is the point in time where something changes, whether the source is connected to a component and it begins charging, or whether the source is disconnected and it begins discharging. But that t equal to 0 is simply where we begin our analysis. The region before that is steady state. It's technically the initial conditions, but we would like to say that the voltage or the current is not changing with respect to time, so we can call it a steady state. And once it reaches full charge, fully charged, it is again a steady state. And this is, of course, the transient portion where it is still charging. Okay, but it's still charging. And so you will see that when we generate the equations, they will all look very, very similar. All right, any questions? Any questions thus far? Okay. So based on our classification, we can have 4 different kinds of circuits, 2 each for natural and forced response. Natural response circuit, simple inductor connected to a resistor, and we have a RL circuit and a resistor connected to a capacitor gives us a RC circuit. Note the subscript. It says EQ. And EQ is simply the total equivalent value of that component. Okay. Schematically, it is only one element, but physically it could be more than one. You could have hundreds of resistors, hundreds of capacitors, hundreds of inductors. But if it is possible to reduce it down to one single element, then it is still one RL circuit, one resistor, one inductor, and one resistor and one capacitor, RL and RC. Okay, and hence the term EQ. So when you look at a circuit, it'll be up to you to determine whether it is a RL, RC circuit, whether it is reducible down to one single inductance and capacitance. And then you can proceed with your analysis. Okay. There is no source in the circuit, and hence it is a natural response. So absence of source, you should automatically think natural response. Any stored energy in that capacitor or inductor will start being discharged. If we do add a source somewhere in there, if we do add a source, then it becomes a forced response, right? It becomes a forced response. The circuits will look like this. So we are adding a source in those same circuits. No difference in that circuit, except now there is a source. This is for RL. This is for RC. And again, as I said, we can solve for both the voltage or the current. And so if we want to solve for the voltage equation, we would draw the Thevenin equivalent circuit as seen by the capacitor or the inductor. If you want to solve for the current, you would draw the Norton equivalent circuit as seen by the component. Because if you have a voltage source, and a voltage source has a bunch of resistors connected to that inductor or capacitor, well, we need to know the exact voltage that is being applied to that capacitor or to that component. If the source is connected directly to that capacitor with only one resistor in series, well, then that's different. This is very important because If you have multiple sources or multiple resistors in a circuit, that would affect the speed of transfer, the speed of energy transfer, right? It would change the time constant, again, which we'll learn about in a few slides. And hence, we need to find the Thevenin or the Norton equivalent circuits as seen by those components. Now, in a problem for chapter 4, the Thevenin and Norton are not going to be that complicated. Okay, it'll be a minor, very small analysis. Not going to be complicated. All right, any questions? Any questions at all? All make sense so far? Yes. Well, Norton circuit will always be in parallel. Norton circuit equivalent is a current source in parallel with the resistance. So this is the Thevenin equivalent. This is the Norton equivalent. Norton equivalent, current source in parallel with the resistor. Thevenin is basically a voltage source in series with the resistance. That also goes back to chapter 1. If you have a voltage source and you want to signify the resistance of a circuit, because the resistance of the source itself will drop some voltage across it. If you have a resistor in parallel with a voltage source, what happens? That voltage does not drop, right? Voltage remains the same in parallel. And so if you have a voltage source here with Vs, and you want to show the resistance of that circuit, well, the resistance of the circuit is drawing some voltage itself. If you have it in parallel, that cannot be true. It has to be in series. And so Vs and Rs. The same thing with the current source. If you have a resistor in series with the current source, well, a current source will supply its rated current no matter what it's connected to its output terminals. So it will transfer Is, no drop whatsoever to the output. The resistor has to be in parallel. All right, any other questions? Other questions? Okay. So let's look at a natural response circuit for RL. Okay. Now, a few things that we have to keep in mind when you perform these analyses. This is a switch or symbol for a switch that we learned about in chapter 1. When you have a arrow either going up or going down, it indicates that the status of the switch is being changed. In this case, the arrow is going up, or at least up in the direction of the closing of the switch. So it indicates that at some point in time, that switch is going to be flipped open, right? The lever is moving in the direction of the arrow. If it's going down, it's going to indicate that it's going to close at that point in time. And the point in time is noted by t is equal to 0. Now, it could be t is equal to 5, t is equal to 4, it could be anything. But for the most part, all the problems that you will look at will always have t is equal to 0. So this basically indicates at time t equal to 0, the switch will flip open. When the switch flips open, the circuit changes. Okay, so you have to redraw the circuit for both t less than 0 and t greater than 0. So t less than 0, the switch is closed, right? It tells you that at t equal to 0, the switch is being flipped open. So at t less than 0, The switch was closed like this. Does that make sense to everyone? And more often than not, you will read the words a very long time. And a very long time simply means that sufficient time has elapsed for the inductor or the capacitor to reach some sort of steady state. Okay, some sort of steady state. So here tells you for t less than 0, the inductor L is short. Why? Because for t less than 0, the switch was closed. The switch was closed for a very long time in the past. We don't care how long it was closed for. We simply need to understand that from those words, a very long time, there is some sort of steady state. In this case, in this circuit, that steady state is the source is connected to the inductor. So what does it mean? The inductor is fully charged. So a very long time simply means it was connected to a source for sufficient amount of time that it has reached full charge. It has reached full charge. And when an inductor is fully charged, it behaves like a short circuit. So what happens? All of the current keeps flowing through that inductor. Does that make sense to everyone? So for transient responses, it's very critical. You have to understand, you have to redraw the circuit diagram for t less than 0 and again for t greater than 0, because there'll be two different circuits. What happens here at t is equal to 0? The switch flips open. When the switch flips open, the source and the resistor R0 are disconnected. The only thing that is left in the circuit is that resistor on the right. Circuit reduces to a RL circuit with no source present in there, and so it becomes a natural response problem. Again, remember, you are asked to analyze the circuit from time t equal to 0 into the future. You don't care about the past. You only care about time t equal to 0 and into the future. In this case, it is only the inductor and the resistor. So if the inductor was fully charged when the switch was flipped, all of that energy is now dissipated in that resistor. All of the energy is now dissipated in that resistor. Eventually, all of that energy will go to the resistor. The resistor will dissipate it as heat, and it will decay to 0. So the energy, which is a finite amount of energy, is all released. So final value of that current will always be equal to 0. So when you have a natural response problem, the final steady state value will always be 0. And that is the assumption you always make when you begin your analysis. If there is no source in the circuit, eventually it will decay to 0. That's the most important assumption to make. A minute left. I want to talk about plus and minus. So plus and minus simply indicates the time right after and time right before. Here we use 0 because we are talking about time t equal to 0, but it could also be any number. It could be 5 seconds, it could be 5 plus and 5 minus. Simply means the time right before plus and right after. Okay, so minus is right before, plus is right after. There is no specific number given to that. The important thing is that right before and right after is used because the current through an inductor cannot change instantaneously, and the voltage across a capacitor cannot change instantaneously. Okay, so think of what it means when you put all of those together here. Switch is flipped at t is equal to 0. At 0 minus, meaning right before the switch was flipped, what is the current in that inductor? Is, because that's the fully charged value of the current. At t equal to 0, the switch is flipped open. Source is disconnected. Now the energy is being discharged to the resistor. So we need to know what the energy is at that point in time, at that beginning point in time, t equal to 0. The t equal to 0 and t equal to 0 plus, meaning right after the switch is flipped, current cannot change instantaneously. So our starting point value of that current in the inductor is also Is. And that's what is indicated by that 0 plus and 0 minus. Okay. Long time in the past, source was connected to the inductor. Inductor is fully charged, has a value of Is. Source is now removed. Inductor begins discharging. That beginning point of discharge has a value of Is. So think on those concepts, review that material, and we'll pick up here again on Wednesday. I will be in my office hours. If you need to see me on Zoom, you please send me an email. If there's any confusion, I need to clarify, so I'll send out a class email. But again, if you need to see me on Zoom, do not just hop on and wait for me. You send me an email, and then I will come online.